Hey, dear friends, welcome to the second session in the focus on ISI CMA entrance exams. So our resource person Lalit is with us. So without any further delay, I think we can move to the session directly. I welcome everyone to this problem solving session. Welcome, Lalit.
Yeah, thank you, sir. So, uh, you all have tried the problems. So, I have sent already the problems in the group. So, I have taken selected problems, okay, from the CM. These are problems from ISI 2019 exam, okay. So, let's start. Uh, so that, okay, by the way, here it is alpha, okay, not zero, alpha. So that limit n tending to infinity, alpha to infinity, this is equal to this. When alpha is greater than 0, but not for alpha equal to 0, right? So this is exchange of limit, okay? So solution, let us consider the case first when alpha is greater than 0. So and consider the sequence of functions f and x equal to this, okay? I want to show that if alpha d, this is an open unit disk, and we have a function which is holomorphic open unit disk to open unit disk, so that f has a 0 of order n at the origin, so that mod of fz is less than equal to mod z to the power n for all z and d. So this is a direct application of maximum modulus principle. So let's start. You have given that f has a 0 of order n greater than equal to 1. Okay, n is greater than equal to 1. So what does this imply, by the way, in terms of derivatives? Answer if you know. If a holomorphic map has a 0 of order n, what does that mean? The nth order derivative would vanish or not?
No, sir.
No, right? So it has a power series expansion, right? N goes to 0 to infinity, a n, z to the power n. But this will comes out to be n is greater than equal to n to infinity. Why this? Do you know? Because, and this an is not equal to 0. Okay. And do you know what is value of an? What is the value of an? In the power series expansion around 0.
Sir, n 0 divided by n factor.
Okay. So this is non-zero. Okay. Keep that in mind. So now define a function. Define gz equal to fz. What do we want to prove? We want to prove that mod of this function is less than equal to 1, right? So we are defining this function if z is non-zero. And what will you define if z is 0? What you should define? Let me know. It must be the limit, right? The G will be holomorphic by Riemann's removable singularity theorem. It must be the limit. Limit z tends to infinity. 0 fz over z to the power n. So to what this limit equals? I have written here everything, right? So to what this limit equals? So make it interactive, okay?
Sir, AN.
Okay, Savas. AN. And this is analytic, okay? G is analytic function on D. If it is analytic, we can use the maximum order principle. So for each disk, say dr with C such that mod of z is less than equal to r, where r is any number less than r, less than 1. Okay. We have by maximum modulus principle, maximum modulus principle. So gz is less than or equal to, so you can say z belongs to the boundary of, right, because the supremum will be attained at boundary. So gz it is equal to, in the boundary, the value of the function. So what you are doing this, okay? So you have this unit disk and you are considering the disk inside the unit disk, okay? The disk of radius r, okay? Hope it is clear, right? You are considering these disks. So on the boundary of these disks, your gz is continuous and its value is this, right? Fz, because 0 does not lie on the boundary of this disk, and g is continuous also, the supremum will also be attained. Okay, so I can write that there exists a zr where the supremum will attain, by the way. So this will be so mod of fz over z to the power n, right? But fz is less than equal to 1, right? Mod of fz is less than equal to 1 and mod of z is less than equal to r. So you get this, right? This holds for each r. Note that for each r less than 1, so at tending r to 1, we get what we get. Mod of gz is less than and equal to 1, right? Therefore, mod of fz is less than equal to mod z to the power n for all z inside D. Okay? You must have seen this before, right? This is just, this is called, what this is called? Schwarz lemma, okay? And you can also do something further, that what happens if equality holds at some point, then your f comes out to be a function of the form cz to the power n, okay? And that is also application of maximum modulus principle, okay? So any questions? So the question number 4, this is the interesting one, okay? You definitely will like it. So to solve this question, you need not to know very much, just differentiability and the existence and uniqueness theory from differential equations. Okay, so let's start. And one thing I want to point out here, that these kind of questions are often asked in different competitive exams. The same question, the same idea will be very, very helpful for you to solve the questions from ODE, CSIR net. I have seen everywhere this kind of question, everywhere. NBHM, TIFR. Yeah, this is ISI. Okay. And in CSIR net, I have seen this a lot of time. this time also, okay? And last time also. Okay, so try to learn this. And the technique to solve the question is same every time. The questions may be different, but the technique is same. So what it says, let f r to r be a C infinity function. C infinity means it is infinitely differentiable such that fx vanishes only if and only if x is an integer. Suppose the function x satisfies this ODE. That means that x is a solution of this ODE for all t in R. So there are two here. A says that if z and the range of x has a non-empty intersection, then so that x is a constant. Okay. The another one says if this is empty, then so that this limit exists and is an integer. Okay, so let's start with first. Is not empty, right? So this implies there exists a T0 in R such that xt0 is what? Xt0 is some integer, right? It is clear. So consider, yeah. Is there any problem? Okay, so consider the IVP xt x dash t equal to f xt, and the condition is xt0 equal to m. Okay, so f is locally Lipschitz, right? Yes or no? Let me know. Is it true that f is locally Lipschitz? Okay, so it is locally Lipschitz and continuous. So this IVP has a unique solution. Okay, IVP has a unique solution by existence and uniqueness theorem. So what is the solution, by the way? Can you see the solution? What do we have to prove, by the way? We have to prove that the solution is a constant. Okay, so can you see the solution? The solution is in front of you. Okay, what is the solution of this IVP? And you are not using something given to you. Reread the hypothesis. F vanishes only if and only if. Yeah, Madhuvanti, do you want to say something?
Yes, sir. I'm saying the same thing.
Huh?
When x is an integer, f of x is 0, we are given x of t naught is m an integer. So f of x naught of t naught is 0.
M is the solution, right? The solution is xt equal to m for each t. Okay, so why? Because see, if you put m here, you get m, right? See, let me verify it, okay, for you. So if you take the derivative of constant, then you get 0, right? Obviously. And on the other side, if you put m here, and you have given that f vanishes when x is, I mean, you can see here, f vanishes when x is an integer. So this is also 0. Okay. So the differential equation is also satisfied. So any questions? We are done with the first one. Okay. Now, this is an empty set. Then so that the limit of xt exists and is an integer. Okay. This is more interesting. So see. Now, is empty means, what does this imply? Can anyone of you let me know? What does this imply?
There is no integer in the range of x.
Yeah, there is no integer in the range. So that's right.
So
there exists two integers. Okay, there exists m such that this is true or not. I will ask you why this is true. Okay. Why? So try to figure it out and let me know why this should be true.
Intermediate value property of x.
Intermediate value property. Right. So, okay. See, let me tell you, xt cannot be an integer. Okay. So it must be between two integers, right? For each t. Yes or no? Two consecutive integers. Try to understand like this. You have integers here 1, here 2, here 3, dot, 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 0, -1. So if a continuous function, this is continuous also, okay? Because this is a solution of a differential equation. That it is differentiable also. So the answer is that xt is continuous. Continuous. Okay. So it cannot be an integer. So if say that choose a particular value t0, okay, if xt0 lies here, then f for each t xt is between 0 to 1. Why? Because xt cannot be here for any t, because otherwise this continuous function has to take 1 also, right? Because of the intermediate value property. Whenever a continuous function takes two values, then it takes every value between them. Okay. Right? Okay. So now, okay, let me ask you something. That can you see that the x is monotone? If yes, raise your hand. Yes, it's a monotone because see, we have given this, right? Xt, since f is 0, fx is 0, if and only if x is an integer. Okay.
Does this mean that between m and m plus 1, f will have the same sign?
Yeah, very good. Sabas. So fxt never vanishes, right? Because xt is never going to be an integer. And being a continuous function, this must keep same sign. Okay. So f this is equal to x dash t, keep same sign. First of all, I have to show the limit exists. Okay, then I will show that it is an integer. Okay, so keep same sign. Okay, this means x is monotone, right? It does not matter which sign it has. So it is either greater than 0 or less than n0. So to see that it is a monotone function, we just need that, okay, that it has same sign when t varies over r. Okay. So if xt is monotone, that means this implies limit xt exists, right? Okay, now it might be infinity, it might be minus infinity, but in the extended plane at least exists, right? Yes or no?
Yes.
Because monotone functions has limits. You may think that it may be infinity, but if it is infinity, so I'm saying that just say that exists means that exists infinitely also, okay? So now can you conclude that it must be an integer? Yeah, by the way, sorry, it is not infinity, okay? It exists. It exists because we have this case, because it is between two integers. So this exists in R. Okay. So can you conclude that it is an integer now? And what that integer, you know that either it will be m plus 1 or m. So can you show that? I mean, can you think of that? I will show it. That what can we use? Okay, so let's think graphically. Okay. So see, suppose that you have monotone and its graph always between these two lines. Okay. So something like this, it may be, right? It is monotone and it can be monotonically decreasing and so on. So what do you think about the derivative? As t tends to infinity, where the derivative should go? What this graph is giving you the information about the limit of the derivative. Yeah. Yeah, please. Yes, Madhuvanti.
0, sir.
Right. But we are not sure it, okay? Because we have just confirmed it from the graph. It may be 0, okay? So I will show it that I will use it, I mean. Okay, suppose limit not m or m plus 1. Okay, so if it is m, then we are done, or m plus 1, then we are done. So, and beyond that limit cannot be, okay? So because xt is bounded between these lines, so xt can go up to m plus 1 and m. Okay, so if not, but it exists, so assume that limit of xt m, and this m is strictly between these, right? From the above discussion, from the above information you have. Okay, so now limit of the derivative, what that comes out to be at t tends to infinity, that is limit right, what is that, this, right? So Fm not 0. That is a contradiction. But let me show you why that must be 0. Okay. So it says that not 0, but on the other hand, okay, let me start with the new page. Okay, so by mean value theorem on this interval. Okay. Because x exists on R, it is given, okay, in the question. Keep that in mind. Sometimes, I mean, whenever you will see other questions in other exam, it need not be, it need not exist over R every time. Okay. So keep that in mind. So here we can use this. By mean value theorem, this should happen, right? I'm showing you whatever I said, just observing from the graph. Okay. So this must be equal to f dash Cn for n. Cn is between n plus 1 and n, right? By mean value theorem. Do you agree with this? Okay. So taking limit on both sides, we get limit n tending to infinity on the other side. So Cn also tends to infinity. Okay. See from this, when n tends to infinity, Cn also tends to infinity. These both limits exist, right? Because we have assumed this. So both are equal to m. Yes or no? M minus m equal to 0. But it contradicts what? That the limit n tending to infinity f dash Cn is 0. It contradicts something. What? Let me know. This thing, right? Because if you have a function and you have this limit that t tends to infinity, limit is n, then it does not matter which sequence you choose, which diverges to infinity, then this must converts to m, right? As n tends to infinity. This is a sequential criterion for the existence of limit. Yes or no? So, huh?
Sir, it is f of c, it is not f dash of c.
No, I mean, not f of c actually. So because for each n, there is a Cn in between. So C will depend on n.
No, I'm saying it's f of c and not f dash of c. Because x dash is equal to f.
Oh, sorry. Yeah. Actually, yeah, it is x dash. Yeah, thank you. And I have, yeah, everything is okay, right? Yeah. So you are right. Thanks for correcting me. Divesh, you wanted to point out the same thing?
Yes, sir.
Okay, thanks. So is it clear, right, that we arrived at a contradiction? At a contradiction. This contradicts, let me say it star, okay? When you will be seeing notes, you might confuse, contradicts star. So it means, so what should happen? Limit exists and must be equal to m or m plus 1. That depends if it is monotonically increasing or decreasing, but we just have to show that it is an integer, okay? Nothing more than that. So we are done. Okay. Do you want to ask something in this question? You will see this question, this kind of question over and over again if you will write the competitive exams. No questions. Okay. This is from function analysis. Let H be a Hilbert space and K be a closed subspace of H. Given any bounded linear functional f k to C, prove that there exists a unique extension f tilde H to C of f as a bounded linear functional satisfying this norm-preserving extension, and that must be unique. Okay, so what do we have to prove? We have to prove that the norm-preserving extension will be unique. By Banach extension theorem, there will be a norm-preserving extension, okay? But we have to prove the uniqueness, okay? So K is a subspace of H by Banach extension theorem. There is a norm-preserving extension. Okay. So existence is this. This shows the existence. Now, K is closed. It's closed. So a closed subspace of a metric space is complete or not? Of a complete, H is complete and K is closed subspace of it. It must be complete, right? So K is also Hilbert. Given a bounded linear functional by Ridge representation theorem, the bounded linear functions on a Hilbert space has a specific form, right? So by Ridge representation theorem, there exists a K belongs to K such that f of x equal to, this is a representation vector, okay? X K, and the norm of f is equal to the norm of representation vector, okay? So now take f tilde be any extension. Okay, I will show that this is unique, okay? Any extension, and this is equal to this, by the way. So extension of f, but again using Ridge representation theorem, again by Ridge representation theorem, representation theorem, there exists a H inside S such that now that S need not be same HK, but we will prove that that is equal to K. That will prove the uniqueness. Yeah, Neha, do you have something to say? I mean, do you want to point out something? Okay, so such that f tilde is of the form, it will for all x inside H, okay, and the norm of f tilde is equal to the representation, norm of the representation vector, okay? So see, this f tilde is extend this function f. Okay, so f tilde must agree with f. We have f tilde is equal to f on, yeah, you can say like that. When we restrict f to k, this is equal to f, right? So okay, for all x inside big K, right? Okay, so small manipulations give you this, right? So what does this mean? H minus K perpendicular to the subspace K, right? So this is small k, okay? If both are looking like same, then bear it, please. So this is clear. So I want to show the extension is unique, and I want to show that this is just, for that I need to show that h is equal to k. So how can I show that h is equal to k? I mean, in the inner product space, norm vector space, whenever you want to say that h equal to k, so there is a way. Prove that its a norm is 0, right? When you want to say so that some vector is 0, then prove that its a norm is 0. So norm of h, we have norm of h is equal to norm of h minus k plus k. This is equal to norm of h minus k square norm of k square. Why? Why this? Tell me. Anyone?
Because h minus k is perpendicular to k.
Yeah, Savas. Because h minus k is perpendicular to k, right? This. So, and their norms are equal, right? Norm square, by the way. And it cancels this, by the way, because they are equal. You know that, right? Yeah, see, look here. Norm of h is equal to norm of f tilde, and this, because we are looking for a norm preserving extension. Okay, I forgot to write it here, that any norm preserving extension, I should have written it, norm preserving. There may be extensions which does not preserve norm. So yeah, we get that this 0, this means h is equal to k. This means that any extension looks like this, okay? So it must be unique, okay? Right? Is it clear? I have taken any extension and so that it is uniquely determined. Shown that it is uniquely determined, okay? So now let's do algebra, okay? We have, by the way, 40 minutes around and 4 questions. I think we will do it within the time. Okay. So let A be a diagonalizable M cross M matrix with entries from C. Define exponential A. When it say define means this limit exists, okay? Yeah, Weber. Do you have some question?
Yes, sir.
Please ask.
Sir, in the last line where we have written that inner product of x with h minus k is 0. So why can't we just directly conclude that h minus k is 0?
No, it is for all, it is perpendicular to k, not to h. K is just a subspace. Because
the inner product is 0 for all x.
Yeah, all x in k, not in h. So why do we, I mean, if you have some vector and which is perpendicular to full of the subspace, say that H is a subspace, then this is also 0. Then we conclude that X is a 0 vector. But this H minus K need not lie inside K. Right?
Okay, because it is a subspace just. K is
yeah.
just a sub.
K is perpendicular over the subspace, not on the full subspace. Otherwise, then H minus K is also perpendicular to H minus K, and the vector which perpendicular to itself is a 0 vector, right?
Yes, sir. Thank you, sir.
So I hope that answers your question.
Sir.
Okay, so let's solve it. Okay, so let me give you some question. Okay, before I need 2 minutes break. So let me give you a question to think that this ideal. Can you find this? You have 2 minutes. Okay, maybe less than that. This ideal is isomorphic. I mean, this quotient ring is isomorphic to. Is it a field? And if it is a field, then how many elements are there? Okay, so just let me do it. Okay, you have 2 minutes. It is classwork. Okay, not homework. I'll back in 2 minutes. Okay, so okay, could you figure it out? What is the answer, Abilipsa?
Field.
Field with how many elements?
25 elements.
Okay, Sabas. Okay, so let's restart. So given, let A be a diagonalizable M cross M matrix with entries from C. Define this. Assuming that A0 is the identity matrix, prove that determinants of this matrix is A to the power trace A. So there exists a P in GL and R, so GL and C, such that A is equal to PD P inverse. Diagonal, okay? Diagonal matrix. So its diagonal elements will be eigenvalues of A, okay? So A to the power n factorial is equal to PD P inverse, right? PD to the power n factorial. Is it clear? No? So
Yes.
this sum A to the power n factorial n goes to 0 to k, say big N, 0 to n is equal to P factorial n goes to 0 to n this holds, right? Taking everything is clear, right? N tends to infinity, we get. So what I said that it is given this. So this means this exists, okay? We have to assume that. So this side we get n factorial. This is given to be e to the power a, defined to be e to the power a. And on the other side we get, what do we get? Like this, right? Yes or no? Can you see that? If you assume that d is lambda1 dot 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 lambda n, that you know that d to the power n by n factorial is lambda to the power n by n factorial. Right? So this sum is looks like this. 1 plus lambda 1 by 1 factorial plus lambda 1 square by 2 factorial dot what n tends to infinity, it becomes e to the power lambda. Okay, so determinant of e to the power a is equal to determinant of p d. I should write it, I mean this matrix. Let me denote this by e to the power d. Okay, is it fine? Denoting this by e to the power d. So this comes out to be e to the power lambda 1 product of all the diagonal elements, and this comes out to be summation lambda I. Okay, what is the sum of all the eigenvalues of a matrix?
The trace.
Trace of A. That is what we need to prove. Okay, so is it clear? Okay, so let's move to the next one. Solution. A is given to be this. So my first question to you, that this polynomial x to the power 4 plus x square plus 1 is reducible or irreducible? Question. Reducible or not? Do it now and let me know. Just raise your hand, okay? If you are able to figure it out. Okay, Ria. Ria, what is your answer?
Sir, it is reducible.
Reducible or irreducible?
Reducible.
Okay, so what are the factors?
Sir, x square plus x plus 1 and x square minus x plus 1.
Sabas. Note that So are you students wondering that how she got this? She might have used something else, but it's not that difficult. Okay, let me show you how do you do this. Okay, so you have to do just this. How? See, x to the power 4, we can write it 2x square plus 1 minus x square, right? Yes or no? And this is x square plus 1 whole square, x square, right? Now you understand. Okay, right. Is it clear? It's not difficult to factorize it. To factorize it. Okay. Okay. Thank you. So have you heard about the Chinese remainder theorem?
Yes, sir.
We will apply it here. Okay. Do we need to apply it here? Okay. I don't think so. We need to apply it here. Okay. So now, can you tell me some ideal of it? Some ideal. Ideal of this ring.
You need to think of those ideals of ZX which contain x to the power of 4 plus x square plus 1.
Right. So please let me know a few. Okay, so by the way, I want to ask you a question, students. So are these co-maximal? These two ideals? Why
R is
they
a commutative ring. R by ij is isomorphic to R by I cross R by j.
No. I'm not asking about the Chinese remainder theorem. I'm just asking that these two ideals, this one and this, are co-maximal in ZX or no?
Yes, sir. Co-maximal.
Why they are co-maximal? How they are co-maximal? So what linear combination gives you the one? To apply the Chinese remainder theorem, that might not need here, but I just want to ask you a question for the sake of question, that are these co-maximal? Obviously, their GCD is 1. They are irreducible. They can be written, one can be written as a linear combination in QX because QX is a PID, but ZX need not. So I'm just asking that whether or not they are co-maximal. So, do you understand my question, students? Co-maximal means if you have two ideals, I plus j is equal to 1. Yeah, okay, let me know if they are co-maximal. Okay, so this is an ideal, right? By correspondence theorem, this is an ideal of the ring. So to solve this question, you should have some knowledge about the ideals of ZX, okay? Then you will be able to do it. Otherwise, you might ask me that why did I pick this ideal? Okay, so because I know the maximal ideals of ZX, and please try this exercise at home. These kind of questions are often asked in interviews also and in exams, that maximal ideals of ZX are of the form Can you complete?
So some prime
Maximal ideal
number,
of ZX of the form f of ideal generated by f of x comma p.
such
And-
that f of x is reducible in ZPX.
Right, very good.
F of x comma ideal generated by
Yeah, right. Irreducible in right. These are maximal ideals, okay, and these exhaust. These are all. So that's why I took it here. Okay, now A by the quotient by this ideal. So and this ideal contains this, right? That's why I did here factorization, because this is a factor of this, right? So any multiple of this is a multiple of this. Okay. So if you, you don't need to take 5 here. Just this contains this. And if you are adding some extra, then that will also contain. So, and why I took 5, you will understand, you will comprehend now. So
I think you took 5 because x squared plus x plus 1 is irreducible in Z5.
yeah, very good. You got it right. Okay. So this. So this is isomorphic too. Okay, I have to write it often. Okay, so it is already denoted by A. So by third theorem of isomorphism, this is isomorphic to ZX modulo right. Third theorem of isomorphism. You might call something else Z, so I just write here by theorem of isomorphism. Okay, you know about it, right? This theorem. So you read about it when you learn correspondence theorem. Okay. So, and this is isomorphic too. This is your homework, okay? Z5x. You can directly define a homomorphism, isomorphism also. And this polynomial is over Z5 now. It is irreducible. This is also your homework. Irreducible.
That's
over-
last one I can't understand. Z of x by ideal generated by x square plus x plus 1 comma
Mhm.
5. How can we isomorphic to Z5 of x? That's why
So what? What is the question?
Z of x by ideal generated by
Huh?
Z of x by ideal generated by x square plus x plus 1 comma 5
Huh?
is isomorphic to Z5 of x by ideal generated by. That is I can't understand.
What you didn't understand?
No, sir, it is
How I
last line is Z5.
okay, this is step.
Yes, sir. Yes, sir. Yes, sir.
Yeah, you can try to figure
Yes,
it
sir.
out. Okay, I said that it is your homework. Okay, that's not difficult. With a little effort, you will get to know it. Just try it. Okay. Or you can just directly define a homomorphism. Okay, try to see that how this will look. So how the element of this ring will look like, then you will see a pattern and you will see that where this some element, specific element should go here. Okay, and that will an isomorphism. Okay, so do it. So now this is a PID. Okay. Yeah, I think I don't need that. This is a PID. Yeah, this is a PID. And this is an irreducible element. I need that. And the ideal generated by some irreducible element is maximal in a PID, right? So this is a field. And field with how many elements?
25.
25 elements.
Right. Field. Okay. Easy to verify. EG check. Z5. AX. AV inside. Oh. So all these cosets are distinct and these are all. So this is maximal. That's why it is a field. So your I is this. Okay. We have to find a I now. So I is this. Take. So, yeah. Is it clear? So do you understand why I put 5 here? I mean, why I choose this specific ideal? First of all, actually, I want to get like this. Okay, that's why. So I thought that does that exist? I mean, can I choose some ideal like that? Here is 5 and some irreducible polynomial and which contains this. Okay. So we have 2 more,
The
right?
5 was necessary because a field with 25 elements will have means the 5 was necessary because a field with 25 elements will have characteristic 5.
Yeah.
So we need the relation 5 equals to 0.
Relation?
The relation that 5 equals to 0.
Yeah. Right. So examine whether there is a polynomial fx in Rx such that this is isomorphic as rings to the product ring C cross C. Here you will need Chinese remainder theorem. Okay. So this is a easy question. Now consider this. Okay. X square plus 1, x square plus 2. This is isomorphic to Rx. Why? Co-maximal. Okay. Their GCD is 1. What? Yeah. Someone said something.
Please repeat this again.
Huh?
Please repeat this again. This is that.
Okay. I'll elucidate. Okay. Wait. So
Thank you.
first of all, observe that their GCD is 1. So Rx is PID. So they are co-maximal. Okay. So first are co-maximal. Co-maximal means their sum is 1. Because their GCD is 1, so you can find polynomials in Rx so that this linear combination x square plus 2, sorry, here x square plus 2 into g comes out to be 1. So they are co-maximal. What I did that consider this, okay, f is this. Now Chinese remainder theorem says that if the ideals are co-maximal, then this is isomorphic to this. This application of Chinese remainder theorem, okay. R, if I and j are co-maximal, then R modulo I j is isomorphic to R modulo I, R modulo j, and the isomorphism is canonical. Okay, which sends R modulo ij to R mod R plus I, R plus j. And this is an isomorph. So I have just applied it. Okay. Is it clear?
Yes, sir.
Isomorphic to C, right? And this is also isomorphic to C. Do you know why? What are the isomorphic? Let me tell you. So define from Rx to C, which takes Fx to Fi. This is called the evaluation map, and its kernel is ideal generated by x square plus 1. Okay, the fundamental theorem of ring homomorphism will imply that, because this is onto homomorphism, that this ring is isomorphic to C. Okay, you must have seen this. If you have done the course in ring theory, you must have seen this, because this is a very basic example. And this is called evaluation homomorphism. Okay, and for the second one, you have the same. I mean, do the same thing, that Rx to C, send Fx to where? F, evaluated in root 2 hours. So you get this, right? So this answers the question. It's not difficult at all. Okay. So now we have the last one. Yeah. So I want to give you a moment to think about it, because it is, I mean, hint is also given. Okay. This is a question which is also asked in CSIR net around 2019. And yeah, this is also 2019 exam of ISI. So try to think it, okay? And raise your hand if you are able to figure it out. Try to use the hint. And you have to prove that they are isomorphic. So you have to define an isomorphic and see that how can we use fundamental theorem of arithmetic, okay? Let me give you 1 minute to think it, okay?
Okay.
Okay. Ria did it. And what about others? Raise your hand if you know the answer already and if you are able to figure it out. I just want to know. Just use the fundamental theorem of arithmetic. Take a positive rational number and see that how can you factorize that. That will let you know that what should be the isomorphism.
Let's
Sakni,
title this book.
yeah. Okay, Neha. Who saw? Bhupesh. Yeah, you said, right? You spoke, right? Okay. So what is the isomorphism? If you have a P, say 2/3, okay, where it should go? In ZX. Neha, where it should map? Where it should be mapped? Okay. Okay, let me tell you. Okay, see. So Q is this. Right? And we have to take positive rational numbers, no? So what I should write here, and here I should write greater than equal to G. Okay? And ZX, you know, the polynomial
is not allowed.
Huh? Did I? wrote
The
something.
group is not allowed.
What is not at all? Not at all?
And P also
Oh.
should be strictly greater than 6.
Yeah. Right. Thank you. Right, took 0 also now. Thank you. So this is a group. We denote it by Q greater than 0. Okay. So ZX is polynomial ring. Okay. And you write the details. So now pick a first, let me say that P1 equal to 2. Just notation for the sake of notations. Okay, I'm writing here. Then I will let you know that how you can think about that. P3 equal to 5 ... right? We have enumerate the rationals. Nth prime, I mean fourth prime is 7. Okay, so pick a P by Q inside Q positive. Then by fundamental theorem of arithmetic, fundamental theorem of arithmetic, P by Q equal to P1 alpha 1. So let me write A1 A2 ... A, where AI are. So Pn right? You can do it. AI may be negative also. Okay, so you factorize P, you factorize Q, then take all the prime powers in the numerator, you get this. Okay, so where you should map that where you should map this, okay, so that the map should be well defined and it is an isomorphism. Okay, so I map to this A1. By the way, I should start with P0. Okay, just for the notations. Okay, I'm modifying the notation. So P2. I am doing this for consistency. Okay, so yeah, so this will map to A0, A1x, A2x square, and ... all the way up to this. Okay, so let me know this is well defined or not. First, map is well defined, right? Because the prime factorization is unique. Because prime factorization is unique. Okay, the map is well defined and it's not really difficult at all to prove that this map is an isomorphism, is an homomorphism, and it's clearly onto, right? Onto is clear, right? And it's also 1 because say that if something maps to 0, clearly onto, and say something goes to 0, P by Q goes to 0. What does that mean? That means P by Q is equal to 1. Don't you think so? No prime divides P by Q, right? This implies, because if there is one prime, at least one prime, which appears here, say 2, then this does not go to 0, right? Because this will go to a polynomial like 2 plus something, right? Okay. So fill the detail, okay? Convince yourself. So this is 1, 1, this is on 2, and please verify that this is an homomorphism, okay? Verify that this is an homomorphism. This map is a homomorphism, okay? So we are done. They are isomorphic. Any questions in this? Yeah, Neha, do you have any question, or you had raised the hand before? Yeah, no questions? Yeah, okay, so I'll stop here.
No, sir. No question.
Yeah, okay. Yeah. I have done all the problems what I have selected. So
So in yesterday's session, you suggested some of the books which we can refer for a study
sorry.
purpose.
Actually, I forgot that I said that I had made already a video in what I had recommended all the books, what I like of algebra analysis and some of topology and number theory. So I will definitely share this video immediately after this session. Okay, I will ask professor to
Sir, I
send it
think
to the group.
my mail ID is not like attached to the group or somewhat because I haven't received the mail for the same.
No. So from where?
Yeah,
Telegram
Neha,
group.
don't worry, we will share it in our group as Lalit shares the link.
Yeah. Okay.
So Lalit, so I think the problems are over now.
Yeah.
Okay. So tomorrow is the IISc exam.
All the best to all.
Yeah. Let us wish all the best to all participants. Okay, thank you, Lalit, for this nice session with a good collection of problems and good interactions. Thank you very much on behalf of Math Aspirants Group. Thank you, everyone, for being here.
Thank you, sir.
If any of you would like to share any feedback or any comments to express, you may make it now. Otherwise, we will wind up here. So, Lalit, I think we can wind up here.
Yeah, okay.
So please do share the link of references that you told that you have arranged, you have processed a video, prepared a video on that. So please do share that. I will share. Okay.
I will share immediately after this class.
Okay. Okay, Lalit. And